Welcome back. I hope everyone had a chance to stretch or do a few jumping jacks, and we're back for the last hour of the symposium. I'm really excited about what's to come. You're in for a real treat. We're about to take a deep dive into computing and sustainability with Meta's Bobbie Manne and Carole Jean Wu. They will discuss the sustainability of the compute backbone required for augmented and virtual reality applications and strategies to reduce the carbon footprint of AI. Their goal is to make the field of computing more environmentally responsible and sustainable. Bobbie Manne is a computer architect at Silicon SoC Innovation at Facebook, and Carole Jean Wu is research scientist and manager at Facebook AI Research. Her work has included building and optimizing systems for machine learning execution at scale. Welcome, Bobbie and Carole Jean.
Thank you so much. So should I go ahead and get started?
Yes, please.
Okay. So Carole's going to be sharing the slides for me. Thank you so much. Thank you very much for inviting us to be here, or inviting me to be here. I'm really looking forward to giving this talk. My background as a computer architect for about 2+ decades in industry. I have worked at companies that most people are familiar with, such as Intel and Microsoft. And more recently, I am at Meta in the Reality Labs group there. So I'm going to start kind of by going historically and looking at what computing has done historically. Carole, next slide. So the last 50 years have seen this tremendous growth in computing. We have advanced from a scenario where there might have been one computer per company to one where there are multiple devices per person. Each individual in the US is estimated to have at least 3 computing devices, and each household has at least about 13 connected devices. And these range from cell phones to laptops to smart assist devices, and more recently, AR or augmented reality and virtual reality devices. Now, supporting these devices is a massive ecosystem that started with the internet that took root in the early 90s, to cloud computing a decade or so later, to much more recently, AI and machine learning. Now, each of these devices, whether it be the one that you carry around with you or in your hand, or the ones that are sitting in the data center, has a carbon footprint associated with its manufacture, use, and disposal. A cell phone, for instance, is around 50 to 70 kilograms of carbon, while the server in the data center can be in the low thousands of kilograms. The IT infrastructure of computing is estimated to account for approximately 3.7% of the world's carbon emissions. And this expenditure is expected to grow as more of the planet's population enters the internet economy. Currently, about 60% of the population has viable access to the internet, but 40% doesn't. So next slide. There is a carbon cost to the computing ecosystem, but that is not the whole story. As Bill Gates noted in his book, How to Avoid a Climate Disaster, carbon emissions can be broken down into multiple categories: plugging things in, growing things, getting around, keeping warm and cool, and making things. And the way we are building and using computing today has a positive impact on all these categories. The section on plugging in, for example, refers to the energy we use for all our electronic equipment, including computing equipment. It accounts for 27% of the total carbon emissions. However, what it doesn't show is how efficient computing has become in the last 50 years. Processors, which are fundamental to all our devices, are over 6,000 times more energy efficient now than they were 50 years ago. Cloud data centers, which host much of our internet-based economy, such as Netflix and Walmart, are massive, but have been shown to be at least 70% more energy efficient than each company having their own server farm. So in addition, the computing infrastructure has also enabled us to grow food more efficiently with better yields and less water, reduce waste in all aspects of our manufacturing processes. And many of you have smart devices that enable more efficient heating and cooling in our homes and our offices. So one of the biggest contributors to carbon emission is travel, whether it be your daily commute or occasional flights. For example, air travel is estimated to contribute as much to global warming as the IT infrastructure. So research in 2020, during the time of COVID, had shown that carbon emissions were lowered by 13% in the US, primarily due to the sharp decline in vehicle transportation in 2020 because of COVID. In addition, it is estimated that 20 to 25% of workforces in advanced economies could work from home, about 3 to 5 days a week, even after COVID. So working from home during COVID or after would not have been possible without the underlying computing infrastructure and devices that we have today. However, the current remote work infrastructure is lacking in how it connects us. We don't quite have that same experience talking to each other as we're doing right now in a two-dimensional forum. Next slide. At Reality Labs, we are trying to make the remote experience even more seamless. So for example, imagine glasses that let you and a coworker pop up a shared whiteboard in a cafe. Or imagine sharing a whiteboard with your colleague in another city and not having to travel there and truly have that interactive and collaborative experience with that colleague. Now, occasionally we do have to travel. So, and for those occasions, glasses, imagine glasses that will enable you to have a virtual desktop anywhere in complete privacy, and not just in complete privacy, but also reduce the number of devices we need in order to be productive. We may no longer need keyboards or mice, for example, in order to have this kind of productive environment. Next slide. So, as I said earlier, all our existing and future computing capabilities require significant investment. Investment in this massive infrastructure that supports all these capabilities. Now, one of the biggest changes we've seen of late is the use of artificial intelligence. AI is essential to enabling many of the capabilities that I talked about earlier, but it doesn't come for free. AI requirements are growing exponentially, and this chart here shows the growth of AI requirements for both training the AI model and for using the model, also referred to as inference. So over the course of 18 months, AI system capacity at Meta data centers has grown by nearly 3x, resulting in an increase of carbon emissions both for the manufacturing and the use of this equipment. So at this point, I'm going to hand it off to my colleague, Carole, who will provide a more detailed view of carbon emissions associated with the AI infrastructure. And thank you again for having me and to discuss this a great topic.
Thanks so much, Bobbie. Hi, everyone. This is Carole Jean, and I'm from Meta AI Research. I'm a research scientist at the AI org. So as what Bobbie mentioned, AI is one of the biggest application driver that we see in the decade and likely for the next decade as well. So let's take a look at what AI's resource footprint looks like today. And then I'll share with you where more work is needed in order to enable sustainable technology growth going forward. So here, from the perspective of the AI model development cycle, we can see we start with data, go into model experimentation. Once model is fully trained with reaching some level of accuracy of desire, we then deploy into production training, where we train with higher quality data, more larger volume data. And then when the model quality is acceptable, then we deploy that for inference phase. Here, we found that the amount of power capacity devoted to the major phases of the machine learning pipeline, namely the data storage injection, model training, and inference prediction phases, is roughly equal. And what that means is that given an industry scale machine learning model, it is equally important to focus optimization efforts at these three different stages of the machine learning pipeline. And so now, to capture AI's carbon footprint end to end, we must also consider the product lifecycle. And so to do so, we use a commonly used methodology called lifecycle analysis. In this lifecycle analysis, there are four major phases. There is the manufacturing, transport, product use phase, and recycling. For the purpose of this characterization study, I'm going to focus on manufacturing and product use in the next couple of slides. So here, we call the energy footprint of AI computation, we translate that into operational carbon footprint. And that is the carbon emission that get produced during the operational use phase of the AI system. And then there is also the embodied carbon footprint that we need to consider. And that is the carbon footprint that is produced during building the infrastructure to enable AI use cases. Okay. So now knowing the sources of carbon footprints of AI, next I'm going to share with you the recent characterization study on quantifying the carbon footprint of important large-scale machine learning tasks. We'll look at the breakdown between training and inference for machine learning tasks, as well as the carbon footprint breakdown between embodied and operational phases. Hopefully, this analysis can help us focus on the biggest piece of pie in terms of optimization effort. So let's start with AI's operational footprint here. On the x-axis, we take a look at the 6 machine learning models that are representative of Meta's production task. There's the universal language model is responsible for multilingual language translation, whereas the DLRMs or deep learning recommender models supports a variety of personalization and ranking use cases. Here, to train a modern language model for Meta's product, it will produce 45.2 metric tons of carbon emission. That is roughly equivalent to 5.4 homes of energy use for 1 year. Whereas training DLRM models will produce carbon emission that's about 9 times higher, okay? So how does Meta's AI training compare with other open source or publicly available use cases? On the right-hand side of the figure are the carbon emission from a recently published paper by Patterson et al. From Berkeley and Google. So here we see that the average carbon footprint for machine learning training task at Meta is about 1.8 times larger than that of a modern conversational agent, in this case called Mina. And as compared to OpenAI's GPT-3 model, Meta's emission from model training is about a third. Taking a step further, once the model is trained, it is further optimized for production deployments for inference. So here we take a look at the additional carbon footprints from the inference phase of the machine learning workload. When looking at the model lifecycle holistically, we found that the carbon footprint of language model is dominated by inference phase, whereas for recommendation and ranking use cases, the model training carbon footprint is roughly equivalent to the inference. While the exact inference number are not available for the open source use cases, but according to the recent study from Google, it is a 40 to 60% split between training and inference. And for Meta, both training and inference can contribute to significant emission here. So that's a story about AI's operational carbon footprint. What does the embodied carbon footprint look like then? In this particular analysis, we look at the additional carbon footprint coming from manufacturing of AI systems. And in this particular figure, it is shown in the green color. Across the same 6 machine learning tasks, we found that the embodied carbon cost is about 50% of AI models' operational carbon cost. And so now when we consider the overall life cycle of machine learning models, manufacturing carbon footprint can be quite significant. And so another important takeaway that we want to keep in mind is that these are the carbon footprint of a single machine learning model, right? The scale of machine learning deployments matter a lot. And so these AI's carbon footprint can add up quite quickly as these machine learning models get trained frequently, and the number of machine learning models get deployed in large scale data centers can add up quite quickly too. So in addition to the cloud deployment environment, another important piece of the computing spectrum is going to come from consumer electronics, where AI can happen quite a bit. So what does the manufacturing footprint of client computing like consumer electronics look like today? Here, we analyze the carbon footprint of computing in this recent work called Chasing Carbon. We found that the manufacturing emission dominates the footprint of consumer electronics. And here, the analysis done by looking at publicly available reports, sustainability reports from Apple. what we see is that hardware manufacturing accounts for about 74% of Apple's overall emission, of which 33% comes directly from integrated circuits, such as the SoC systems on chip, DRAMs, or NAND flash storage. In comparison, the operational use for Apple's device accounts for 19% only. Okay, and here the vast majority of client computing's environmental footprints comes from manufacturing. And if we take a look at the carbon footprint across different generations of iPhone, in this particular example, using iPhone 3 from 2009 to iPhone 11 from a decade later as an example, during this decade, we see that we see about 1.6 times reduction in iPhone's operational carbon footprint, while the manufacturing footprint has increased by about 3 times. And this is coming from more advanced hardware architectures getting incorporated into the modern consumer electronics. We have more GPUs, DSPs. We even have neural processing unit being implemented in these latest generations of consumer electronics in order to enable AI, more efficient AI processing, and all of that adds up in terms of manufacturing footprints. And so now it is particularly challenging to amortize these additional embodied carbon footprint because client devices are most often underutilized. And it is this unique usage pattern that's going to introduce new system design opportunities from the perspective of environmental sustainability. Furthermore, there are over 50 million metric tons of electronic waste that were generated worldwide in 2019. And so this is, again, has significant implications on how we design the next generation consumer electronics. How do we embed design modularity into as the first design principles for this future electronics? So to conclude our talk here, in the past 50 years, we have witnessed impressive technology advancements. Seeing significant environmental implications of AI computing today, we want to look at and focus on opportunities such that we can achieve environmental sustainability going forward. So here are 3 things I would like our community to focus on. First is that characterizing and analyzing carbon emission is quite a complex process as compared to what we are familiar with power modeling, performance measurements, energy measurements. So while they are standard ways to measure power consumptions of AI system, there isn't a metric or easy to use tools yet to that enable us to standardize carbon footprint measurements, not to even mention other environmental emissions of computing. And so so first we need a tool, and then to scale the growth of computing technology sustainably, we also need the design tools for us to assess the environmental footprints of hardware design, of systems that we're going to build. And then we have to put environmental sustainability as the first class design principle when architecting next generation computing infrastructure. And specifically, to support the dramatic growth of technologies and AI, we have to innovate sustainably and deploy technologies in an environmentally responsible manner. Thanks so much for your attention. It's our great pleasure to be here and share some of the work at Meta with you.
Thank you so much, Bobbie and Carole Jean. That was really a fascinating presentation. We appreciate you sharing these key challenges to reduce the energy requirements for AI development and the carbon footprint we should be considering across so many dimensions of computing. I love the analysis, and it's really fascinating and a basis for a lot of great future research.